record and share the screen, and then get my PowerPoint going. And hopefully I can make the PowerPoint go like that. Yeah, and then make it bigger. Oh. All right, well, this will do, I suppose. So is that the first slide? I think it is. Yeah, all right, so yeah. The idea that I want to sort of just get through today, and it's not a lot, I should be in front of the video, I suppose, but the idea that I want to get through is that there's a different way of thinking if we want to solve problems using computers. And that's the idea of this course. The idea of this course is solving problems with computers. And so that is a subset of a bigger idea, which is just solving problems. And so actually, if you learn the skills to solve problems, then you'll also be a little bit better and ready to solve problems with computers. Does that make sense? Now, where it's a subset or the added difficulty of solving problems with computers, and I think I tried to indicate this in our first lesson, is that solving problems with computers, we have to sort of narrow down or get rid of a lot of the, I guess you could say like common sense, intuition, things that we use a lot in our normal problem solving and daily mode. We can't really use those so much in computing. And that's because computing's limited ability to do things. And so we have to be a lot more, well, you could say precise. Precision is what we need. That we have to be very careful in the way that we construct our problems and the solutions to those problems. So people started thinking about this idea. We got this term computational thinking as a way for people to think about how we approach a problem so that it can be solved on a computer. And actually, this guy, Seymour Papert, in 1980, sort of coined this term, procedural thinking. And basically, the idea being that we need to learn how to formulate problems so that a computer can solve them, and automate the problem so that a human doesn't have to do all of the calculating, for example. So that's the idea there. Now, hold on. Just pushing the button isn't making anything happen here. Internet is unstable. Let's go to the next slide. Is that going to go? Oh. This is annoying. As I said, today's a bit of a... Okay, that's slide 3. Wow, so bad. Oh, I thought I was missing something. All right, so have I... these are probably worth less. This is slide 2. History of computing. Did you see on D2L, I put 2 videos. I'm not going to show those videos in class today because you can, they're not my videos. To be honest, I Googled and I got some, these look good. I put them for you. Just to give you some background, okay, on the history of computing. And that's probably the start of most sort of computer college courses or textbooks. And it's nice, light, entertaining reading, I suppose. But we go back to like 1650 or something. Babbage made an engine that was able to do computations, mathematical computations. And then I think Mohammed might have mentioned this in our class before. Alan Turing in the 1940s made another sort of machine, but also got some electronics involved in it. And that's where we really took off with our computing. Once we got electronics involved in the thing, and we got a tube which could go on and off. That was in the 1940s, and then that was replaced by transistors in the 1960s. I mean, if you're interested in that stuff, a lot of that was driven by military and space. So the transistors that greatly reduced the size of the on-off switches, and that was required if you wanted to put space ships, because you needed computers on those spaceships. And spaceships, it costs a lot of money to put weight up there. So if we could reduce the size of the on-off gates, then you could be more successful in space. And so that we got the transistors in the 1960s, and it really took off from them. And then, of course, we got the silicon chips that sort of came out of that idea of the transistors. And that's where we really got into, you probably heard of Moore's Law. Moore's Law, basically, in the 1965, this guy named Moore came up with this law, which was basically that every 18 months to 2 years, the cost of a certain amount of computing would be half, or for the same amount of money, you could get double the amount of computing. And that was pretty much a true rule for most of the time between now and then. We are coming up to some limits with heat, with processors and things like that. And so there's some issues there, but no doubt it'll get back to that. And there's all kinds of sort of new technologies that come to make it faster. The idea here that we're supposed to introduce in this class is there's some things that can be computed and there's some things that can't. And I kind of mentioned that a minute ago when I mentioned that there's lots of things that we think when we're using our intuition, all right? When we're being sort of using, you could say, common sense. You know, you could put two ideas out there that seem to make sense to us, but if it's not very, very precise, won't work with a computer. And so there's some things that cannot be computed. So we try to sort of stick to those things, obviously, that can. That's where the precision comes in, that we have to be very precise. We do have a textbook. Now, when I say we do have a textbook, I don't have a hard copy of this textbook in my hand. What I was able to do is, and you could do this too, I found a book, an online bookseller that gave me a copy with a 30-day free trial and $8 a month after that, or something like that. I mean, I don't know that you need to. Usually we don't make textbooks, mandatory, but this is actually quite a readable book. I think you'd find it. It's not at a very, very super high level that it's going to sort of catch you in your English or anything like that. It's kind of a nice book, so I do recommend it. And actually the first couple of chapters is where I got a lot of this stuff that I'm just going to talk to you about today, which is okay. So this one I've already mentioned. Okay, so then this term came up, as we say, computational thinking, or we've reduced that to CT. And so these are some of the components of computational thinking. Computational thinking includes logical thinking. All right, so you can do a degree in logic, right? All right, logic is sort of a crossover between mathematics and philosophy. So philosophers, they spend a lot of time talking about logic, and so do mathematicians. And of course, IT. In IT, because we have this concept of logic gates, and we have the concept of logical operators, and we'll just talk about that in a minute. Now, by the way, all of these, I'll put this PowerPoint up on D2L with a lot of other things as well later. So decomposition. The idea of decomposition is if you have a big problem, it's kind of hard to solve it. Just starting, where do you start? So what you do is you break the problem down into components, and then you solve each of those components, and then those components can be plugged in together to make the larger solved problem. All right, so that's the idea of decomposition. Very, very important in computing. Now, I won't say that all computing people always have used decomposition. It's certainly improved computing from its original sort of manifestation, I guess you could say. So our modern computing, we certainly use decomposition. It's the idea behind modules and functions, and which is very important in your computer programming nowadays. So what we do is we get the smallest unit that will run with a set of parameters passed in and out, and we code that, we get it right, and then we can use that over and over again. And that's modularization or producing functions. Generalization, the idea there is if we see a pattern, so last week, last thing that we did on Thursday is I gave you some little logic critical thinking problems. Remember that? So we started off with the L-shaped things. Pretty soon you could see a pattern, right? That's the idea, right? You see a pattern. When you see the pattern, then you can start breaking that pattern down into something that we could work with. We ended up with a formula from that, didn't we? 2n plus 1 or something like that. And so that's the idea there is, can we recognize a pattern, something that's repeatable? That's where computers are really, really useful, right? If we can repeat something, computers can repeat things really, really quickly and really precisely and accurately. So if we can isolate the pattern, that's where the human mind comes in, right? To identify the pattern and put that into some kind of code, start out with a pseudocode, and then that gets translated into some kind of computer language, and then we solve our thing. Modeling, the idea is that where we're looking at something complicated and we just get the simplest representation of it. And so when I say that, all right, so if I say I had a model car or a model plane or a model person, the idea is that we look at them and we can see features of the real thing that we want, but we just got the simplest idea of it that will represent it. Oh, I spelled abstraction wrong. That was a bit of a hurry, I guess. Abstraction sort of follows from that idea. Abstraction is going from something that's not well defined to something that's very, very carefully defined, but in the least or simplest way possible to define that. Evaluation, I hope that makes sense, is that where we're looking at various data and coming to some kind of judgment on it. It's horrible talking with a mask. I don't know. So I've made this point a couple of times in this lesson today that about precision. That is very important in our computing, that we get things precisely. Computer will not tolerate ambiguity. Ambiguity means where something is said or represented, and it could mean more than one thing. All right, computer won't tolerate that. And so with the computer, we must have something which is definite. Now, yeah, I mean, we can use probabilities, in which case we're using a special kind of logic in our computing. Look, we've got a few more slides. I won't keep you all day on this. We're going to use logic in computing. And so in our logic, we're going to, and this logic is the same for, as I said, for philosophy, for mathematics, and comes into computing. So we have premises. If something is a premise, then it's something that can be either true or false. It's not a maybe. Premises are either true or false. And so we start with our premises. If we have premises that are true or false, then we can come up with a deduction. A deduction is something that, because this is true, so that's and, right? So now we're talking about logical operators. Because this is true, then it follows that that is true. That's a deduction, okay? And it only works if, as I said, the premise is true or false. Induction, that's slightly different, okay? And so what we're doing in induction is we're working with something which is not necessarily 100% true or 100% false. With those types of things, we use our logic to do induction, and that would be things like probability. Like there's 100 balls in this container, and 99 of them are red and one of them are white. Each of you takes a ball. I could induce that it's probable that you got a red ball, but it's not certain, right? Because you might have got a white ball. You know what I mean? But it's probable that you got a red ball. That would be induction. And so with our logic, we're using some operators like this. Have you seen these before? Sure, huh? Sure, yeah. And so with and, the two things that are on the either side of the and, they must be true for the statement to be true. So the statement including an and can be true or false. But for it to be true, both things on either side of it must be true. If both things on either side of it are true, then it is a true statement. If either of the things on either side of the and are false, then the whole statement is false. Does that make sense? That's an and. Or how it works is you have two statements, either side of the or two conditions, either side of the or. If the or is, if both of them are true, then that statement is true. But if either of them is true, then that statement is true. But if either of them, if all of them, in order for it to be false, they both have to be not true, right? If either of them is true, it's true. So there's two ways that it's true. Not, what it just does is whatever the not is applied to is inverted. So if the thing was true and you put a not on it, then it becomes false. If the thing was false and you put a not on it, then it becomes true. Does that make sense? So not just inverts. Then we have these two other sort of things which work with implications. We have if. So if basically works, if this condition is true, then this happens. If and only if is very similar, but how if and only if works is, if this thing is true, then this happens. But it also means if this thing is true, then that happens. You can go backwards with if with the double F if. Double F if we say is biconditional. Yeah. So we have some terms for those. When we use the and in a statement to make a condition, we call that conjunction. That's where two things must be true for the statement to be true. Where we use the or, we call that disjunction. That means only, even if only one of them is true, then it's true. And where we use the not, we just say that that inverts. And so lastly, we're talking about the if, the two ifs. This is conditional. If something is true here, then this other thing will happen. And it's unidirectional. That means that it doesn't work backwards. Whereas the if and only if is biconditional. The thing that happens because of this can also tell you that that thing must be. And so so I'll give you an example of that. I'll try to if my car,
Excuse me, sir.
you know what, I'm not going to give an example. I'm sort of a bit flustered at the moment, so I'll come up with that later. Okay, ask me for an example of if later. I'm going to pause for a second now, for which you'll be.
Excuse me.
Yes.
Sir, can you let my friend in? He's waiting in a room.
I'll try. So this is the problem is, all right, it's probably on participants. Yeah, there we go. Okay, so let me just pause. What do I want to do? I'm going to stop the share. And screen sharing, stop the share. All right, so stop the share. Don't need that anymore. And let's pause the recording.